Hello students, I am Dr. Nimi Singh. Today I bring you the next learning episode in BSc Forensic Science on a very important unit of the paper Technological Methods in Forensic Science, that is the forensic microscopy. This is going to be the second part of forensic microscopy in which we are going to study about the electron microscopy. In the first part, you were introduced to the concept of microscopy where you had studied about its principle, components, various types of microscopes and applications of microscope in forensic science. Today, in this lecture, that is the part 2, you will be studying about electron microscopy in details. You will also be acquainted with the principle of electron microscopy and its types, that is the transmission electron microscope, the TEM, and scanning electron microscope SEM. Lastly, we are going to wind up this module by studying the various applications of electron microscopy in forensic science. Dear students, let us have a look at the modules which we are going to study today. The first one is going to be an overview of microscopy, then we will shift on to electron microscopy, then principle of electron microscopy, the types of electron microscopy, transmission electron microscope and scanning electron microscope in details, then the applications of electron microscopy in forensic sciences, and then we are going to conclude this lecture. Dear students, today it becomes imperative to revise what we studied in our last lecture about microscopy. Hence, with this in mind, we will just have a quick study regarding the overview of microscopy. So, let us come to the overview of microscopy first. A microscope is a well-defined optical apparatus that uses an arrangement of lenses to yield magnified image of small objects. To achieve this, a stereo microscope uses a number of mechanisms that gather light and transmit the light track so that a magnified image of the observed object can be focused within a short distance. The discipline of examining small things using an instrument is known as what we are going to study, the microscopy. Microscopic means undetectable to the naked eye if not assisted by a microscope. There are numerous types of microscopes. An optical microscope is the most up-to-date and the first manufactured microscope which utilizes the light to image the sample. Electron microscopes are another category of microscopes which comprise of transmission electron microscope and scanning electron microscope. The first microscope to be technologically advanced was the optical microscope, though the originator is not easy to recognize. The primary microscope was believed to be made in 1590. Giovanni Faber coined the word microscope for Galileo's compound microscope in 1625. The optical microscope, time and again referred to as the light microscope, is a kind of microscope which involves the visible light and a coordination of lenses to enlarge images of small samples. Optical microscopes, they are the elementary design of microscope and were actually designed around 1600. Elementary optical microscopes can be very simple, although there are countless multifaceted designs which intends to have advanced resolution and sample contrast. Factually, optical microscopes were easy to improve and are prevalent because they use visible light and as a result the sample can be easily observed by eye. The image from an optical microscope can be taken by standard light sensitive cameras to produce a micrograph. Initially, images were taken by photographic film, but contemporary improvements in CMOS and later charge coupled device cameras permit the storing of digital images. Only digital microscopes are now accessible in which a CCD camera is utilized to analyze a sample and the image is displayed directly on a computer screen devoid of the requirement for eyepieces. A substitute to optical microscopy which does not apply visible light comprises of scanning electron microscopy and transmission electron microscopy. There are two rudimentary arrangements of the conventional optical microscope. The simple one with just one lens and compound with many lenses. The immense preponderance of present study microscopes are compound microscopes, while some economical commercial digital microscopes are simple single lens microscopes. Principally, a magnifying glass is a rudimentary single lens microscope. In general, microscope optics are stagnant. To concentrate at diverse focal depths, the lens to sample distance is adjusted, and to receive a wider or a narrower field of view, a separate magnification objective lens should be applied. Most up-to-date research microscopes also have a separate set of optics for illuminating the sample. Let us come to the electron microscopy. Now, electron microscopes are scientific instruments that use a beam of extremely energetic electrons to study objects on a precise scale. This examination can produce information about the topography, morphology, composition and crystallographic information about the object. Light microscopes had certain limitations, as the physics of light to 500x or 1000x magnification and a resolution of 0.2 micrometer, instigating thereby the development of electron microscopes. In the early 1930s, this theoretical limit had reached, and there was a scientific aspiration to comprehend the fine details of the interior structures of organic cells like nucleus, mitochondria, etc. This required almost 10,000 x and above magnification, which was just not imaginable using light microscope. Electron microscopy has been further classified into two types: transmission electron microscope and scanning electron microscope. The transmission electron microscope was the first type of electron microscope to be developed and designed accurately on the light transmission microscope, except that a focused beam of electrons is used as a replacement for light to see through the specimen. The transmission electron microscope was devised by Max Noll and Ernst Ruska in the year 1931 in Germany. On the other hand, the first scanning electron microscope was found in the year 1942, with the first commercial instruments coming in around 1965. Its delayed development was because of the electrons behind scanning the beam of electrons through the sample. Most microscopes can be classified as one of the three basic types, which are optical, charged particle, that is electron and ion, or scanning probe. The electron microscope uses an electron beam to create an image, with electromagnets acting as lenses. The limit of resolution is improved by a factor 1000 over the light microscope. The transmission electron microscope produces two-dimensional image of an ultra thin section by capturing electrons that have passed through the specimen. The degree of interaction between the electrons and the heavy metal specimen influence the kinetic energy of the electrons, which are collected by the fluorescent plate. The light of fluctuating intensity produced is directly proportional to the electron's kinetic energy and is used to produce the image. The transmission electron microscope is useful for studying a cell's interior and its ultrastructure. A scanning electron microscope is used to make a three-dimensional image of the specimen surface. Coming to the principle of electron microscopy. Now, electrons accelerated to a particular potential possess the same wavelength which constitute a more or less monochromatic beam. The beam of high energy electrons, it interacts with the specimen within a certain area of cross section depending upon the electron beam energy. An accelerated electron penetrates into the electron cloud of an atom and its path is deflected, causing it to scatter at an angle. Now, in some cases even complete backscattering can occur, generating the backscattered electrons. Electron microscope utilizes all such interactions occurring between the matter and the highly accelerated electron incident on it. These transmitted electrons are focused with the help of electromagnetic lenses, and the very short wavelength allows the specimen to be imaged with a very high spatial resolution as compared to the light microscope. Now, highly accelerated electrons are able to transmit through a thin specimen and are used for the formation of the image in transmission electron microscopy. These electrons can be transmitted unscattered through the specimen, else can be scattered elastically or inelastically. In elastic scattering, the incident electrons are deflected from the original path and scattered by atoms in the specimen in an elastic fashion without any loss of energy. Such electrons leave the sample with almost same kinetic energy and velocity as was possessed by it initially. However, the trajectory of the electron may change after interaction with the specimen. An elastic interaction involves transfer of energy from the incident electrons to the sample, so that the energy of the electron after interaction with the sample is reduced. These scattered electrons are then transmitted through the remaining portions of the specimen and can be analyzed by using magnetic lenses to form a configuration of spots, each spot corresponding to a specific atomic spacing. This pattern can then yield information about the orientation, atomic arrangements and phases present in the area being examined. Thick specimen does not allow incident electrons to transmit through, instead result into interactions in same plane, generating electrons with diverse energies. These electrons are used for imaging in scanning electron microscope. Now, some of the electrons and radiations generated as a result of the matter electron interaction and which are used in electron microscopic images have been discussed below. The first one is back scattered electrons. Now, the electrons reflected back after colliding with the specimen by elastic scattering through an angle greater than 90 degree are called back scattered electrons. These electrons can be distinguished on the basis of their high kinetic energy as they escape from the sample with energies quite equivalent to the primary beam energy. The fraction of primary electrons that escape as BSE is given as a back scattering coefficient, which varies directly with the specimen's atomic number. The higher the atomic number elements cause more production of BSEs and appear brighter than lower atomic number elements. Therefore, BSE images show contrast in different parts of the specimen having different average atomic number. Then we have the secondary electrons. During inelastic interactions, the incident electrons may transfer their energy to the outer shell or valence electrons. These electrons are electrostatically weakly bound to the nucleus and need only a small amount of energy to overcome the binding force and to eject out into the vacuum. These are called secondary electrons. Most secondary electrons eject with a very small kinetic energy, that is below 50 electron volts. Therefore, only those which are close to the surface, that is generated only within very small depth, are able to escape into the vacuum. Due to this reason, SEs are utilized by SEM imaging to study topography of the specimen. The secondary electron coefficient is calculated as the average number of secondary electrons produced per primary electron. Then we have is the inner shell ionization. The incident electron passing very close to an atom might transfer a part of its energy to an inner shell electron. However, for ejection, these electrons require large amount of energy as they are strongly bound to the atom. If the accelerated electron possesses enough of the energy for its ejection, the inner shell electron is ejected as high kinetic energy secondary electrons. Then you have the characteristic X-rays. In the process of ejection of an inner shell electron, a vacancy is created in the lower energy shell. In order to amend the energy imbalance, an electron from a higher energy level drops to fill the electron hole in a lower energy level. This is usually accompanied by emission of an X-ray photon having characteristic energy depending upon the difference between the two energy levels which are involved in electron transition. Then you have is the Auger electrons. Auger electron emission is another mechanism of stabilizing the atom after inner shell ionization, analogous to X-ray emission. Emission of a core electron occurs by acquiring high amount of energy from incident electron, leaving the ion in a highly excited state. This ion rapidly tends to decline back to a lower energy state by emission of an Auger electron, doubly ionizing the atom. The void formed in an inner shell is filled by an electron tumbling from a higher shell, and the energy liberated in this process is simultaneously transferred to another electron which may emit from the atom in the form of Auger electron. Then you have is cathode luminescence. Now, when a crystal is bombarded by high energy electrons, one or more electrons from the lower energy valence band are promoted to the high energy conduction band. While returning to the ground state valence band, they may be temporarily trapped for a short while, that is for microseconds, into some extrinsic or intrinsic traps made due to impurities or structural defects in the lattice. The loss of energy occurring while leaving this trap, usually in ultraviolet, visible or infrared region, will give rise to luminescence. Types of electron microscopy. The first one is the transmission electron microscope. Transmission electron microscope is particularly meant to study thin specimen which allows the incident electrons to traverse through after due interactions. These interactions are translated into signals which are then magnified and focused on imaging device such as phosphor screen or a CCD camera. The lighter areas of the image represent the thinner sections of the specimen through which greater number of electrons were able to pass, while the darker areas reflect the dense regions of the object. This technique allows visualization of samples on a molecular level, allowing topographical, morphological as well as compositional studies. TEM produced two-dimensional images of high resolution of the order of nanometers and magnification ranging from 102 to 106 times, enabling to image planes and columns of atoms. The instrument can also be used to produce electron diffraction pattern for crystalline studies. Now, the components of transmission electron microscope imaging system are illumination system. The illumination system comprises of an electron source, a thermionic gun which emits monochromatic beam of electrons. This beam of electrons possesses kinetic energy high enough to traverse through the thin areas of the specimen. Electron source inside the gun is a pointed hairpin shaped tungsten filament or a spike shaped lanthanum hexaboride source housed in an electron accelerating chamber. The filament is connected to a high voltage supply about 200 to 300 kilovolts, which heats it up to about 2700 degree Kelvin, the temperature sufficient for thermionic emission of electrons from tungsten. Immediately after the emission from the cathode, electrons are accelerated to their final kinetic energy by applying an electric field parallel to the optic axis. Most of the accelerated electrons are absorbed by the anode plate and only 1% pass through the fine hole. Therefore, the beam current in a TEM is typically 1% of the emission current from the cathode. Then we have the condenser. The electron gun is followed by a condenser lens system that converges the illumination and produces an almost parallel electron beam which is incident on the specimen in the form of a spot. In order to achieve good contrast and wide range of magnification for viewing very small to larger objects in the specimen, most of the electrons that pass through the specimen should fall within a certain diameter corresponding to the screen. Then the stage. The specimen stage holds the specimen perpendicular to the optic axis. The specimen is placed on a ring shaped grid and inserted through an airlock into the chamber which is evacuated before the specimen enters the TEM column. The sample is held stationary during imaging, although it can be displaced in 3 planes and tilted to an angle up to defined distance or degrees with the help of the holder adjustments. This helps to align a particular region of specimen into the path of the electron beam so that all possible regions of the specimen can be visualized. Then you have is the objective. It is an electromagnetic lens made of coils which encounter high excitation current and produce the magnetic field to focus the electrons. The focusing power of lens depends on its excitation and is susceptible to even slight variations in the current. Therefore, highly stabilized current supply is required for accurate focusing of the specimen. The coils of lens utilize high voltage and generate large amount of heat, thus are kept under insulation and are provided with thermal distributors. Then you have intermediate lens and projector lens. The intermediate lens produces patterns in the back focal plane of the objective lens, which is used by the projector lens to form image on the screen. The projector lens produces a large image of several centimeters diameter across the fluorescent screen. The projector lens has a focal length of a few millimeters, which serves to minimize the image distortion occurring due to high angle scattering of electrons. Then you have is the TEM screen. Detectors and image recorder. A phosphor screen converts the diffraction pattern of electrons into visible light signals. The screen is made up of fluorescing material zinc sulfide. As it receives the electrons focused by the projector lens, it proportionately emits light in visible range. TEM is coupled with detectors which generate electrical signals proportional to the photon intensity. These signals are transformed into image which can be seen directly on the monitor or can be captured by a camera. Then comes the scanning electron microscope. SEM, as you can say, it requires low kinetic energy electrons which need not penetrate deep inside the sample, instead interact on the surface up to a few nanometers of depth. The electron source is tungsten filament or an LaB6 cathode housed inside an electron gun smaller than the one used in TM. The electron beam is accelerated by low voltage between 2 to 50 kilovolts. The SEM column and sample chamber are at a moderate vacuum of about 10 to 5 to 10 to 7 torrs, 10.3 to 10.4 pascals to allow the electrons to travel freely from the electron beam source to the sample and then to the detectors. Since the technique does not require accelerating the electrons much, a strong magnetic field is not needed, and therefore the magnetic lenses used are also smaller. A two-stage lens system is placed below the electron gun, which comprises of condenser lens and objective lens. The condenser lens narrows down the electron beam to a spot of about 0.5 to 5 nanometers in diameter that scans the specimen. The final lens is an objective lens which focuses this very small probe onto the specimen. The specimen is mounted on a stage which holds it stably while allowing it to move in horizontal and vertical axis, tilt or rotate, so that all the areas of the specimen can be scanned. The beam now passes through pairs of scanning coils located near the end of the column, which deflect the beam in the x and y axis to perform a scan over the sample surface. The signals generated as a result of due interactions in the form of SEs or BSEs etc. are detected for each position in the scanned area by an electron detector. Now, different signal intensity are displayed as patterns of varying brightness on a cathode ray tube, corresponding to the morphology of the sample surface area scanned by the beam. The electron detectors predominantly used in SEM imaging are scintillator type, also known as Everhart Thornley detector, meant for secondary electron imaging, and solid state detectors for backscattered electrons. Coming to the applications of microscopy in forensic science. There is no crime without clues. Even the most expert criminals tend to leave behind traces of crimes they commit. There may be cartridge cases left at the scene of crime or damages made with the crowbar, handles of the door, etc. Besides the classic fingerprints, the preparators of crime tend to even leave behind hair or fiber traces. Forensic investigations aim at examining these crucial evidences left at the crime scene and analyzing them accordingly. Microscopic examination and analysis of evidences provide valuable results in crime scene investigation. SEM provides superior results and hence are used in many areas such as gunshot residue analysis, investigation of gemstones and jewelry, firearms, identification, that is bullet markings comparison, filament bulb investigations at traffic accidents, handwriting and print examination forgery, examination of paint particles and fibers, counterfeit banknotes, examination of non-conducting materials, trace comparison, high resolution surface imaging. The transmission electron microscope is used in many areas including nanotechnology, gemology, forensic science, etc. TEM gives topographical, morphological, compositional and crystalline information of the specimen being analyzed. The images obtained helps to visualize samples at the molecular level, thereby helping in analyzing the structure and the texture. This information is important in study of metals and crystals, but also has an industrial application. Let us now conclude our lecture. A microscope is well defined as an optical apparatus that uses an arrangement of lenses to yield magnified image of small objects. Electron microscopes are scientific instruments that use a beam of extremely energetic electrons to study objects on a precise scale. This technique has been further categorized into two types: transmission electron microscope and scanning electron microscope. Both of these techniques are used for examination purposes in different fields, including that of forensic science. With all these information, here we come to the end of today's lecture. Do keep in mind what we have discussed today. I will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQs, quizzes, LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.